Hello students, welcome to EPG Pathshala. I am Reema Gupta from University of Delhi. Today we are going to discuss about the module that is Defect Chemistry Part 2, and this is from the paper Ceramics. So students, let us see what we are going to learn in this module. First of all, we will be learning about defects and thermodynamics. Next, we will be discussing about equilibrium concentrations and lastly, an analogy to dilute solutions. So before moving further, let us discuss some basic concepts. So all solid contains defects where the ideal lattice as described in terms of an infinitely repeating unit cell is broken. Defects can have a large effect on a range of properties of the material such as mechanical strength, electrical conductivity, corrosion and chemical reactivity. Defects may be formed due to thermodynamic effects and these defects are known as intrinsic defect, or it is due to the imperfection in stoichiometry which are not due to thermodynamics and which are known as extrinsic defects. Some of the defects which are localized in space, that is those which occur at single sites in a crystal, are known as point defects. Whereas extended defects are those which penetrate through the crystal in one or more dimension. So, if we talk about non-stoichiometric compounds, the compounds with incomplete lattices are those compounds which exist with variable composition but which retain essentially the same structure. The continuity of the structure over the whole composition range can be seen from the fact that the position of the peaks in the X-ray diffraction pattern do not change with the composition. Whereas if I take the example of titanium oxide, that is TiO, so TiO is a metallic conductor with the rock salt structure and it occurs with the stoichiometry in the range of TiO 0.7 to TiO 1.25. So the range is 0.7 to 1.25 where it occurs with the stoichiometry. So if we move further, this variation in composition is accommodated in vacancies in either the oxygen or titanium lattice sites. So in the stoichiometric TiO, that is titanium oxide, only 15% of cations and anion sites are vacant and hence this compound has an unusual high concentration of Schottky defects. However, this is complicated by the fact that the defects tend to cluster due to the interaction between the vacancies and also the formation of metal-metal bond within the defect lattice. So in general, if I talk about the formation of non-stoichiometric compounds is common with D, F and some P blocks metal with the soft anions such as S2- that is sulfur and also with the harder anions such as O2- that is oxygen. So non-stoichiometric compounds with anions such as fluoride F-, Cl-, chlorine, sulfate SO4 2- and NO3- are much less common. The first topic is defect concentration. Let us consider the formation of Frenkel defect in an halide, that is Mx. So the guiding equation will be Mm plus Xx gives Vm prime plus Mi star plus Xx. So the changes in free energy that is delta G, depends upon the formation of N, that is Frankel defects pair, at an expense of delta GF energy per pair. So the equation becomes G minus G naught is equal to delta G, which is equal to N times delta GF minus T delta SC. Here delta SC is the change in centrifugational entropy and it is positive, whereas G is the free energy and N is the Frankel defects pair. The equilibrium concentration of defects is found by minimizing delta G with respect to N, that is, the concentration at which the free energy is minimum. Now let us find the defect concentration. So the change in entropy, that is SC, is given by delta SC is equal to K ln W, where W is the number of ways in which the defects can be arranged. Now, as per the defect reaction shown above, the number of Frankel pairs, that is N, would lead to the formation of equal numbers of interstitials which are represented as Ni, as well as vacancies which are represented as Nv. So N is equal to Ni is equal to Nv. Now assuming that the total number of vacancies are equal to N. So the number of ways to arrange the vacancies, that is WV is equal to N factorial divided by N minus Nv factorial times Nv factorial. So the number of ways to arrange the interstitial, assuming that N lattice sites are equivalent to N interstitial sites. So Wi becomes Wi is equal to N factorial divided by N minus Ni factorial times Ni factorial, where Ni correspond to number of interstitials. Now the total number of possible configurations becomes W, which is equal to Wv star into Wi. Now the entropy change can now be represented as delta SC is equal to K ln times N factorial divided by N minus N factorial times N factorial into N factorial divided by N minus N factorial into N factorial, or it can be written as the square of N factorial upon N minus N factorial into small n factorial. So the 2 comes in front of the expression and the expression for the entropy change becomes delta SC is equal to 2K ln N factorial divided by capital N minus small n factorial into small n factorial. So for large values of capital N, Stirling's approximation, that is natural log of n factorial, is equal to n log n minus n. So this can be applied in the above expression and the entropy change expression becomes delta SC is equal to 2K bracket start capital N ln capital N. So here ln is the natural log. So n natural log of n minus n natural log of n minus n natural log n bracket close. And the total free energy can be expressed and is shown in the next slide. Now the expression for the total free change is given as delta G is equal to N delta GF minus 2KT bracket start N natural log N minus capital N minus small n natural log of capital N minus small n minus n natural log n. So this equation comes out to be N naught GF minus 2KT bracket start N natural log N minus N plus N natural log N minus N divided by N. So students, you can see a figure below this expression showing the equilibrium vacancy concentration. Now, if vacancies were stable defects, then at certain concentration, the free energy change has to be minimum, which is shown in this figure, and this corresponds to delta G max. Hence, at equilibrium, we can safely write that the first derivative is 0. Now, as we discussed in the previous slide, at equilibrium, delta Gn means first order del of delta G by delta N is 0, means the first derivative of the Gibbs free energy change with respect to N is 0, and capital N minus small n can be assumed to be approximately equal to capital N, since the number of vacancies is much smaller than the number of lattice sites in absolute terms. This results in n minus capital N is equal to exponential minus delta GF by 2KT. Now we assume that delta GF is equal to delta HF minus T delta SV, where delta HF is the enthalpy of Frankel defect formation and delta SV is the vibrational entropy change. Hence, using this equation, we can further simplify this equation and can write small n by capital N is equal to exponential minus delta HF by 2KT into exponential delta SV by 2KT. Now, assuming that the second term, that is exponential delta SV by 2KT, is approximately 1, as the vibrational entropy change is very small, and hence the final expression becomes n by capital N is equal to exponential minus delta HF by 2KT. Here, delta HF is the enthalpy of Frankel defect formation. Similarly, for Schottky defects, you can all work out that small n by capital N is equal to exponential of minus delta Hg by Kt times 2, that is 2Kt. Now comes the intrinsic and extrinsic defects. We are aware about the intrinsic and extrinsic. So in case of intrinsic defects, the defects which can be determined from the intrinsic defect equation and is temperature dependent are intrinsic behavior. So there is increasing behavior with increasing temperature. Whereas in case of extrinsic behavior, the extrinsic defects are the defects caused by the impurities consisting of equivalent cations. The defect concentration depends upon the impurity concentration, which is constant and is independent of the temperature. So only at very high temperatures the intrinsic behavior again dominates, and the crossover temperature depends upon the defect formation energy. Now comes the thermodynamics of defect reactions. Till now, we are aware about defect reactions. So, a defect reaction can be treated like a chemical reaction, allowing us to relate the thermodynamic variables like partial pressure of oxygen, temperature, to Gibbs free energy change or the enthalpy change, which can be determined using the experimental techniques. So, for a chemical system consisting of N plus, N2 and so on till Ni moles of constituents 1, 2, 3 and so on till ith, the partial molar free energy of ith constituent is given as del of G by del Ni at constant temperature and pressures is equal to Gi bar, which is equal to mu I. Now imagine a defect reaction as a chemical reaction. So the reaction is small a times capital A plus small b times capital B gives Cc plus Dd. So here free energy change can be written as delta G is equal to delta G naught plus RT natural log of A Cc times A dd divided by A AA times A BB, which is equal to delta G naught plus RT natural log of capital K. So here delta G naught is the free energy change which is in standard state, that is at unit activities. So at equilibrium delta G is 0. So the expression becomes delta G naught is equal to minus RT natural log capital K, where K is the equilibrium or reaction constant at the equilibrium. So capital K is given as ACC times ADD divided by AAA times ABB. In addition, free energy can also be expressed as delta G naught is equal to delta H minus T delta S at equilibrium, which is equal to minus RT natural log of capital K, which we have calculated above. So here capital K is K naught exponential minus delta H naught by R, and K naught is delta S naught by R, which leads to the equation which is given in the next slide. So the expression of K becomes capital K is equal to K naught exponential minus delta H naught by R, where K naught is delta S naught by R. So this leads to the equation K is equal to K naught exponential delta H naught by minus R with negative sign. So where K naught is delta S naught by R and R is the gas constant. Alternatively, we can write D natural log K divided by D times 1 by T is equal to minus delta H naught by R, and this is valid for the dilute solutions. So this is an important outcome as it shows that we can treat the defects in a solid as solutes in a solvent. So students, let us summarize what we have learned in this module. So in this module, we have discussed about the point defects which are thermodynamic defects and hence are stable. Next, we have discussed about the defect concentrations. So the defect concentration is strongly dependent on the temperatures as it has exponential dependence on it. Hence, higher the temperature, one can expect very high defect concentrations. Moreover, we have learned that the defects can be created in a similar way as one treats the solids consisting of small amount of impurities. That is, dilute solutions, which is a relativistic situation as defect concentration is not too large considering the fractional concentrations. So in this lecture, we learned about the defect equilibrium of a defect reaction in stoichiometric and in non-stoichiometric oxides. Then in non-stoichiometric, if we talk about, it is observed that there is a strong dependence of the defect concentration. Whereas in stoichiometric oxides, the defect concentration is independent of partial oxygen pressure, whereas they both are strongly dependent in case of non-stoichiometric conditions. So the nature of dependence is governed by the nature of defects present. So by writing appropriate defect reaction and considering the limiting conditions, one can determine the dependence of defect concentrations on partial oxygen pressure, that is PO2. Thank you.